In this video, we solve problem 11.5.509.xp from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to find the point of intersection of the line that passes through the point x equals 1, y equals -5, and z equals 1. And it also passes through the point x equals 5, y equals -12, and z equals 6. We want the point of intersection of the line that passes through those 2 points and the plane given by this equation. Now, I don't know exactly what this plane looks like, and I don't know exactly what that line looks like, and graphing that line in a 2D version of 3-dimensional space and graphing the plane in a 2D version of 3-dimensional space probably won't help us even guesstimate where that line crosses that plane. But I can sort of draw a cartoon. I can draw a picture of it. So there are actually 3 possibilities. We're told that this line actually intersects this plane, so that's helpful. But when we're dealing with lines and planes, there are 3 possibilities. One is that the line actually lies in the plane. So maybe from some perspective, the plane looks like this, or part of the plane looks like this, and the line lies in the plane. That's one possibility. If that's true, every point on this line would be represented by x of t, y of t, and z of t, where x of t, y of t, and z of t are given by the parametric equations of that line. So we'll have x of t equals something, y of t equals something, and z of t equals something. And generally we say, if this line passes through the point x naught, y naught, z naught, when t equals 0, x, y, and z are all equal to x naught, y naught, and z naught respectively. And then there's a direction vector associated with this line. Usually we call that direction vector v. And we say it has components a, b, and c. If I take the components of a, b, and c, or a, b, and c, the components of v, and I multiply them by a scalar t, and then I add those to x naught, y naught, and z naught, when t equals 1, I end up over here. When t equals 2, I go that length of the vector again. And when t equals 3, I go the length of the vector again. If t equals -1, I'd go backwards 1. Like backwards 1 unit of the length of the vector. And as t takes on all the possible values between -infinity and +infinity, we get the entire line. So these are the parametric equations of the line. And we also have the equation of a plane. Now, normally with the plane, we would use a normal vector with component form a, b, c here as well. But we don't want to do that because we're using a, b, and c for the direction vector of our line. So I'm going to make the normal vector, I'm going to represent it by capital A, capital B, and capital C, just to distinguish it from the lowercase a, b, and c, the components of the direction vector of the line. Now, the plane has this equation. If the normal vector is a, b, and c, the plane would have an equation a times x plus b times y plus c times z equals some number, which I'll just call d. So this is the equation of the plane. Now, this is true in general, but if that line lies in the plane, what that tells me is that x of t, y of t, and z of t always satisfy this equation. So I can replace x with x of t, and I can replace y with y of t, and I can replace z with z of t. And if I simplify that, I'm going to cancel out a bunch of t's, and I'm going to be left with d. Because if this line lies in the plane, well then x of t, y of t, and z of t have to satisfy this equation for all values of t. So if I plug those in and I just get a true statement, d equals d, when I'm done, then the line lies in the plane. So let's write that down. If a times x of t plus b times y of t plus c times z of t equals d for all values of t. So that means you simplify this and you get a true statement. All the t's are gone and you end up with a d on this side equals d on this side. Then the line lies in the plane. Oops. Okay, so that's one possibility. Now another possibility when you're dealing with a plane and a line is that this line doesn't lie in the plane, but it lies in a parallel plane. So maybe our plane is down here. This is the plane that we're interested in. And then there's some other plane up here. It's parallel, so they have the same normal vector. And this is our plane. So the first possibility is, oops, I don't know why I drew that so crooked. The first possibility is the equations, or the parametric equations of the line satisfy the equation of the plane all the time. Now, here's the next possibility. In this case, the equations of the parametric equations of the line never satisfy this equation. So when you substitute x of t, y of t, and z of t into the equation of the plane, you're going to get some number. I don't know what it is. I'm going to use p, where p is not equal to d. So if you substitute x of t, y of t, and z of t into this equation of the plane, and you get a statement that's not true. So when you're done, you simplify this left-hand side and you get 3 and the right-hand side is 5. Well, 3 doesn't equal 5. If that happens, that means that the line doesn't lie in this plane, but it lies in a parallel plane. It lies in the plane ax plus by plus cz equals 3, if that was a 3 over there. And remember what we talked about earlier when we were studying planes. If we change this constant, that's essentially moving that plane. Every time we change this constant on the right-hand side, it's giving us a different plane. The normal vectors are the same, so it's just giving us a parallel plane, but changing that number on the right can move that plane up and down or backwards and forwards, depending on how it's oriented in space. But you get the idea. So if, let's say, substituting the parametric equations of the line into the equation of a plane, results in a statement that is never true. Then the line lies in a parallel plane. So this is the plane with the equation ax plus by plus cz equals d. And this is the equation, or this is the plane, excuse me, with the equation ax plus by plus cz equals p, where p and d are not the same thing. So if p and d are not the same thing, and the parametric equations satisfy this equation rather than this one, then the line lies in a parallel plane. Now the third possibility, which is the one that is discussed in this problem statement, is this. Well, if the line does not lie in the plane for all t, and it doesn't lie in a parallel plane, there is some point at which the line has to cross that plane. So I've got a plane down here. And then I have a line in space. And maybe it looks like that. Well, if it doesn't lie in the plane itself and it doesn't lie in a parallel plane, there's got to be a point where it crosses. And I'm going to call that x of t naught, y of t naught, and z of t naught. So there's some value of t where the parametric equations of the plane, or excuse me, of the line, satisfy the equation of the plane. But at all other values of t, it's not going to work. So we're just trying to find that value of t. Once we find that t value, we can think of that as a time. We can imagine a little particle traveling along our line at different times. It's at different locations. Once we solve that equation for t, that tells us what time that little particle would cross through this plane. But it doesn't tell us the location. To find the location, we've got to substitute that t value or that time into the parametric equations of the line. Okay, so this is what will happen if x of t, y of t, and z of t satisfy the equation of the plane at only one value of t. So if a times x of t plus b times y of t plus c times z of t equals d for a single value of t, then the line passes through the plane at this location. Remember, you want to think of t like time, and you want to think of x, y, and z like locations. Now, t doesn't have to represent time. It's just a parameter. It's just a scalar. But thinking of it as time is helpful because it sort of, well, it separates that dimension of time from the three spatial dimensions. Okay, now in our problem statement, we were told the equation of our plane is x minus y plus z equals 6. And we weren't given the parametric equations of the line, but we were told that there are 2 points on the line. I'll call that one x equals 1, y equals -1, z equals 1. And I'll call that one x equals 5, y equals -12, z equals 6. Well, in order to solve this problem, I need to find the parametric equations of the line first. That's my x of t, y of t, and z of t. And then I need to plug them into the equation of the plane. And then I need to solve for t if possible. If all the t's disappear and I get d equals d, that means the line is in the plane all the time. If all the t's disappear and I get like a nonsense statement like 3 equals 5, well, that means the line is never in the plane, it is in a parallel plane. Or if I get t equals 5, that's telling me that at time t equals 5, or at that particular value of the parameter t equals 5, that line is crossing through my plane. So I can plug that t equals 5 back into the parametric equations of the line, and that can give me the location that is associated with t equals 5, and that is the point where the line passes through the plane. Okay, so that's the plan. We just need to find x of t, y of t, and z of t, the parametric equations of the line. And remember how that works. You just use x naught, y naught, and z naught right here. That's any point on the line. So you could use this one or this one, doesn't matter. And then we also need a direction vector with components lowercase a, b, and c. Whoops. Okay, so I think I'm going to use this as my x naught, y naught, and z naught. It's arbitrary. You could just as easily have used that one. So x naught, y naught, and z naught are 1, -5, and 1. And then we need the direction vector of the line. Now this wasn't given to us, but we can easily find it by finding a vector that goes from this point to this other point. Let's let that be our v. So the vector from this point, which I'll call P, to this point, which I'll call Q, can be found by taking the coordinates of Q and subtracting the coordinates of P. So we start with 5, oops, let me leave more space there, -12 and 6. I don't need that comma yet. And now I'm subtracting the coordinates of P. So we want to subtract 1 and subtract -5 and subtract 1 again. And of course, 5 minus 1 is 4. This is -12 minus a -5, so that's -12 plus 5, or -7. And then 6 minus 1 is 5. So that's our A, B, and C. So we're going to add 4t here, and we'll add -7t here, and we'll add 5t here. So this is great. We've got the parametric equations of the line now. Now we want to find the value of t where these parametric equations satisfy this equation of the line. And we're told that the line passes through the plane. So we know we're in this case. But in theory, maybe the line would lie in a parallel plane. If we get a statement like this, it lies in a parallel plane. Or in theory, that line could actually lie in the plane the entire time. Then this would be true. We'd get d equals d. This would be satisfied for all values of t. But based on the problem statement, we know we're dealing with this case. So we're going to substitute these guys into this guy, and we're going to solve for t. Easy breezy. So I had x minus y plus z equals 6, and I'm substituting in my parametric equations. X equals 1 plus 4t, y equals -5 minus 7t, and z equals 1 plus 5t, and we're setting that equal to 6. So we'll simplify by distributing the negative. We don't really need the parentheses there. Negative times a negative is a positive. And I've got 4t plus 7t, that's 11t. 11t plus 5t is 16t. And then 1 plus 5 plus 1 is 7. And we'll subtract 7 from both sides. Ooh, it's going to be kind of an ugly fraction. That's okay. And t equals -1/16. Now you are asked for, let's look at this, the point of intersection of the line with the plane. This is giving me a t value. It doesn't give me a point of intersection with the plane. It doesn't give me a point. I need an x, a y, and a z. So to find the corresponding location, I'm going to take my parametric equations, which were 1 plus 4t, that was my parametric equation for x, -5 minus 7t, that was my parametric equation for y, and 1 plus 5t, that was my parametric equation for z, and I'll substitute in -1/16. And then we'll simplify, and those are the coordinates of the point where that line passes through that plane. So we'll have 1 plus 4 times -1/16, and I get 3/4. And then I'll have -5, and then I've got a -7 times a -1/16, so that's +7/16. I'm adding 7/16. So I get negative 73 over 16. And then the last one, I have 1 minus 5 over 16. So that's 11 over 16. So what is that location? That's x, y, z equals 3/4 negative 73 over 16 and 11 over 16. Now we know, provided our parametric equations are correct, we know that these three coordinates satisfy the parametric equations of the line. Let's just check and make sure they also satisfy the equations of the plane. I should be able to take x, subtract y, and add z and get 6. If I've done everything correctly, when I add these together, I'm going to get 6. Or when I do the x minus the y plus the z, I should get 6. So let's see. We'll do 3/4 minus y, which is negative 73 over 16, plus z, which is 11 over 16. Hey, I do get 6. So that's a very good sign. So hopefully I didn't make any mistakes when I came up with the parametric equations of the line. Provided I didn't, I'm good to go. This definitely satisfies the equation of the plane. If this is right, it also satisfies the equation of the line, and that is the location. This right here is 3/4 negative 73 over 16 and positive 11 over 16. That's where that line crosses that plane.